So this is the second year running. Unfortunately, I have to replace Jian Lee, so best wishes to Jian. Hopefully if she comes next year, she will turn up. But anyway, I mean, there are good reasons that she cannot be here, so best wishes to her. So this morning, so for that reason, this presentation was a little bit last minute. So bear with me. Some of these slides will come as a surprise to me as well as to you. And so I will have to think about what I will say. So we're going to talk about temporal correlation for ARAIM, also a little bit for SBAS. So we have been working on this topic a little bit this year, based on some of the work that was done initially by the IIT, Illinois Institute of Technology. So the first thing we need to remind ourselves is that our requirements for integrity in civil aviation are operational, meaning that we have a risk assigned at the operational level, but our algorithms are run on an epoch by epoch basis, so we must make some kind of allocation, transition from the requirement at the operational level to the requirement at the algorithmic level, which is run on a per epoch basis. So there are, depending on the system that we are being used, if we see the figure on the right, this is not really a real allocation, this is just a kind of abstract representation that when we are in the fault-free mode, as is the case for the SBAS protection level, then generally what has been done is that a number of effective samples is used to divide the operational requirement into even blocks, which are then applied at the epoch level. But whereas in the case of ARAIM, so integrity monitoring, autonomous integrity monitoring, the assumption was taken that the full operational integrity risk can be applied at the per sample basis. So we have tried to look at whether how this may be done for ARAIM, and of course in ARAIM the situation is a little bit more complex. In ARAIM, as we'll see on the later slide, we have a situation where we are trying to handle all the fault modes at once. So we have a multiple hypothesis approach. We are looking at the risk from both the fault-free case and also the cases where we have faults. So this is different to the SBAS and ARAIM, where we just had in SBAS the fault-free case, and in ARAIM we just had the faulty case. We now have to deal with how to do this allocation when we have the fault modes together. So briefly, look again at the SBAS case. So in the SBAS case, if we have a shorter time constant, so our errors are correlated over shorter periods, then this in fact effectively leads to a higher risk that we are going to exceed a threshold, or in this case the protection level. So if our position error our position error shown in green here is to exceed our orange bound, then we are not meeting our requirements. We are having an unsafe condition. And so with the same level of standard deviation, the same variation, if we have a shorter time constant, this increases the chance that we will exceed our threshold within one operational period. Now, the assumption taken within SBAS developments, within the integrity concept SBAS, was, or at least for the current SBAS, single frequency, single constellation, was to take 6 minutes correlation time from the dominant ionospheric error source and divide 1 hour by this figure and get 10 independent samples. But the work that was done by IIT suggested that this simple allocation of simple division of our period of operation by the period of our correlation time is not perhaps appropriate, and that if we are generating errors with respect to a Gauss-Markov model, which is the one that we assume for most GNSS error sources, then 10 is an underestimate of the number of effective samples. So we have computed this a more accurate estimate of this number of effective samples to be greater than 10, and in fact would then lead to an inflation of the protection level for SPAS of around 10 to 20%. And we can look at this impact on performance. In fact, effectively this increases our K factors, which we use to compute our protection levels. These are some simulations for LPB 200, and we see it's not a huge difference, but there is a reduction in the coverage that we can expect when we take into account this more accurate model of the correlation. So in SPAS, we don't have to consider the monitors, because here we are looking purely at the impact at the user level, at the protection level, at the user. But when we go to ARAIM, we have to consider the impact of both the position error, but also the impact on the tests. So earlier I mentioned that we have to deal in ARAIM both the fault-free case and the faulty modes. So here, the top equation represents our probability of hazardous misleading information, basically our integrity risk, the risk that we have a fault and we are not detecting that fault, and that fault leads to a unsafe positioning error. So the first term is the probability of that situation given that we are in the fault-free mode, which we call H0, and the other term, the summation term, represents the probability that we are in that situation. We have hazardously misleading information given that we are in a fault mode Hj. And we have the prior probability of Hj as a coefficient to that probability. So then we have to sum over the number of fault modes that we are considering, NH. Now, the baseline approach to this problem has not considered the number of effective samples, and so we are essentially we've essentially applied the operational integrity risk to each sample. But if we wish to try to account for this effect in a similar way as we've done on the previous slide for SPAS, then one possible way would be to introduce a term, the number of effective samples, for each of these integrity risk terms. So in the case of the fault-free mode, we'll have something similar to the SPAS situation, a similar number that we would expect. But in the faulty mode, we need to ask ourselves, how can we determine this number of effective samples for when a satellite or multiple satellites have failed? Okay, so now we're going to look a little bit about what happens when we have a fault is detected in ARAIM. So there are two possibilities. First possibility is that we detect that a failure has occurred, we isolate that a satellite or a number of satellites are faulty, and we exclude them at that time t. Then at the next time, 1 second later, we are going to reassess whether the satellites are faulty or not. So the question is, do we re-include the satellites that were faulty at the previous epoch, or do we say, no, they were faulty 1 second ago, so we still think they are faulty? Now, the current baseline approach, that is also in the standards for RAIM, and has been taken forward in ARAIM, is to instantly re-include those satellites, not to consider that they are faulty for a long period of time. This doesn't mean that receiver manufacturers couldn't do that. I think, as far as I'm aware, that this is possible with regards to the standards, but the assessments that have been made on the research side have considered that we are going to re-include the satellites at the next epoch. Of course, if that satellite is still faulty, we will more than likely still detect that it is faulty at the next epoch. So we consider this first case, and I call this first case instant re-inclusion. So that means, therefore, that we have, first I'm going to look here at what happens with regards to the test statistic and the effect of the temporal correlation on the test statistic. So these two diagrams on the left, we have the situation where our test statistic takes the value at the green dot at the very first epoch. So it is below the threshold. We are not detecting a fault. But since we are going to, in this mode, re-include satellites that are faulty, it's possible that later on during the period of operation, during the 1 hour, that for this particular satellite or set of satellites, our test statistic begins above the threshold, and so we are excluding that satellite 1 epoch at a time, until at a later time the error drops below the threshold. At that point, we are then going to re-include that satellite or set of satellites. So if we are going to consider temporal correlation, we have to consider that both of these situations, we have to consider the risk that not only at 1 epoch do we have the situation that the test may not detect the fault, but we have to consider the possibility that at a later time during the operation, we also do not detect the fault. So this approach is good for availability, probably good for continuity, since we are always going to re-include the satellite, but potentially could be detrimental to integrity, since we could, at a later time, re-include this satellite. Okay, the second approach, when we are here, I'm going to call operational exclusion, is that if we detect the satellite is faulty, we exclude it for a period of time. Here we have chosen to exclude it for the period of operation that we are considering. So for example, for horizontal ARAIM, 1 hour period for RNP type operations. So this would be, we do not need to worry about the fact that at later times the satellite is going to re-include it because we are excluding it for the whole period of operation. So the integrity risk that we compute for that 1 hour, we will not have the terms that were given on the with respect to the right figure here. So this approach is beneficial from the integrity perspective, since as soon as we detect a fault, we have removed it, but less good for availability and continuity. So in order to compute our risk, we need to sum the possibility that we have a hazardous misleading information, i.e. that our position error, E here, is bigger than our protection level, L, and at the same time our test statistic is below the threshold, K. And we need to consider that this may happen at any point during the operation. This is where we have this big union over I. And in order to be a little bit more explicit, we need to consider the maximum of this over the, well, at least this is one approach. We need to consider that we at least bound the impact of the worst case fault. So mu here is our fault vector. We need to make sure that when this value is at such a value that the probability is maximized, we are bounding that risk. In this work, we've assumed that the worst case situation is when we have a fault on our satellites which is constant through the entire period of operation. We think this is the worst case, but this is something that we have conjectured and not proven as yet. So I don't want to dwell on this. I don't have that much time, and I'm going a bit slow, so if you have any question about this, you can ask me afterwards. So let's consider what is the risk when we are instantly re-including the satellites. So the traditional argument with regards to ARAIM is that when we consider the single epoch risk on the right-hand side, probability that we have a failure which leads that the test statistic, the mean of the test statistic would be, because of the failure, above the threshold. So the risk that we do not detect that is going to be the risk that the noise brings us below the threshold. So that's what's on the right-hand side, that we have the noise from the mean brings us to the green point below the threshold. The argument being that this will be bigger than the likelihood that we are below the threshold and we remain below the threshold through the entire operation. Now, of course, with instant re-inclusion, we have to consider that, as I mentioned before, we have both the risk that we are below the threshold at the beginning, but also that we are going to be below the threshold at a later point during the 1 hour of operation. Furthermore, we also have to consider the impact on the positioning error. So it's not just a test statistic. What determined our risk here was the impact of the position error and the test statistic. So we have to consider what is the impact on the position error as well. So we have to consider that there is the probability that the noise on the position error will lead us to be above the protection level, or we may at the first epoch, or it may be that this happens at a later epoch. So we may not have a positioning failure at the beginning, but after a certain period of time, our position error may then pass above the threshold. So this risk of these two possible situations will be greater than the risk of just a single epoch, that we are above at the first point. Previous work has shown that the noise, or rather the statistical component of the position error and the test statistics, these two elements are independent. So we can take the product of these two probabilities, and of course this will be bigger than the product of the two probabilities that are just a single epoch. So this is saying the multiple epoch risk product is bigger than the single epoch risk. Okay, I should speed on a little bit. So here, this is not so important. I just want to, I'm making a transformation here. On the right-hand side, we have what's called the slope diagram. So this is representing the test statistic versus the position error, and it's a upper left quadrant, which is the risky situation when we have a position error exceeding the protection level, but our test statistic is less than the threshold. We are not detecting that fault. So we want to know what's the probability that at some point during the hour we are in this upper left quadrant. To simplify the diagrams, we make a transformation that puts this top left quadrant to the top right. Or at least the idea was it's simplified, but when we are short on time, it's maybe not such a good idea. Anyway, this means that then we have our equation before becomes the equation at the bottom. So this says that the probability that we have a hazardous misleading information, that we are in the dangerous quadrant at the beginning, or that we pass at some point during the hour into the dangerous quadrant, is bigger than the probability that we are in the dangerous quadrant at the beginning. Okay? So what we want to do is we want to determine this probability on the left, because the probability on the right we already have from the baseline algorithm. So that is the work that we have been doing. So in fact this work is mostly been done by Eugene, who is in the room here. He's been computing these risks as a function of the size of the bias that we are considering. And here we see on the right-hand side, the kind of situation that we can expect, that we have in red the probability of misdetection or probability of hazardous misleading information as a function of bias, so magnitude of the bias along the x-axis, and in blue we have the risk of the all-epoch risk, basically the left-hand side. And so the number of effective samples, the number of samples that we would have to consider in the equation I gave at the beginning, the NES, would be the ratio of the maximum of these two. Well, this is at least one way to define this. There could be other ways, but this is the most natural way to define this value. Okay. Now, what we have done so far, or the assessment that we made in this aspect, also was done, I don't have the time to detail that, but it was done in a way that did not account for the simultaneity of the two processes. So here you can see that the middle line, we have the probability of single epoch, probability of all epoch that our test statistic passes below our threshold, and the probability that our position error exceeds our protection level at some point during the period of operation. But we also need to consider that these two things happen at the same time. Because if we have positioning error at some point, if we have a positioning failure at some point, but it's not the time when our test statistic is below the threshold, then we do not have a risk. So PV here is just taking into account the probability this is happening at the same time. And we have found that this is approximately equivalent to the period of operation, so 1 hour, divided by the time to alert. So here we're in fact saying that we have an independent sample every TTA. So this is not good news, because it means that we have a large NES, but there is a bit of a caveat here. That is that we are considering the probability, the ratio, so maybe let me drop back to this slide. We consider here the ratio of the all epoch risk in blue compared to the single epoch risk in red. However, the baseline algorithm is not using this maximum of the red. In fact, it's allocating more of its integrity risk budget to this fault mode. So it's not as bad as this seems. And in fact, the figures on the bottom right here is that the allocation is much higher than the risk of the single epoch. So one possible way is if we can try to assess offline the relationship between the all epoch risk to the allocated probability, then we would not have to include this detrimental number of effective samples, which will ultimately lead to a drop in availability. Am I in a rush? Or okay. So these results, they are initial results, so I should say that we still have further work to validate this. A lot of this work is based on some numerical integration and some empirically derived distributions, and small differences in these distributions can lead to very different values that we get afterwards. One point we should say is that IIT, they've also been working on this, and they have also fairly large values for the number of effective samples using a different methodology. So that at least provides some validation that we have a relatively large value for this NES. But further results are needed to validate. So it means that we need to find a way to mitigate this, modify the algorithm or modify the justification in some way. Potentially we need to exclude a fault for longer rather than instantly re-include it, which I'll come to on the next slide. Or we could try to justify a prior probability for the very worst case, the fact that we have this worst case fault for the entire 1 hour of operation. Or, as I mentioned in the last slide, we could try to utilize the fact that the allocated probability is bigger than the computed one for the single epoch. Okay, so now I'm just going to talk briefly about the operational exclusion approach. So when we are excluding the satellite fault for longer than just one sample. And in this situation, we need to consider the times at which our events are taking place. So we have, on the top figure, we have the position error E versus the protection level L. And so at TE greater than L, this is when we have a positioning failure occurring. Of course, we have a time to alert margin there between when that happens and when we need to be able to detect and exclude it. So only do we have a positioning failure when this position error exceeds the alert limit and endures for at least the TTA. On the second figure, we have the test statistic versus the threshold for detection, and there we mark here the time that we are detecting the fault. So, of course, what we're concerned about here is what is the risk that our protection level is exceeded before our test statistic exceeds our threshold. Now, of course, in most cases, when we have a fault, as soon as the fault occurs, the test statistic is above the threshold. So these diagrams are a bit disingenuous in the fact that we are showing a situation already where at the beginning the test statistic is below the threshold. Whereas, for the most part, we were going to detect the fault immediately. So what we're concerned here is the probability distributions of the time of first passage. Basically, the time it takes for us to pass a threshold given an initial value and a boundary. So we are following two approaches, one which is theoretical, semi-analytic approach, and also an empirical approach for deriving these distributions. These distributions look a little bit like this. We have a PDF which starts off very low, goes up and then decreases slowly. But of course there is an initial mass of probability that at the very first point when the fault occurs, our distribution is such that we are above that the test statistic is above the threshold, for example. Okay, so given these distributions, we need to compute the probability that our detection occurs after a positioning failure has been present for more than the time to alert. So considering these times of detection and time of positioning failure, we must integrate the orange region, ready orange. But we have this bound of the TTA. Of course, the positioning failure must be present for at least the TTA. And so the latest results, in fact the results that we got yesterday at 10 p.m., because we knew that we had to provide this presentation, suggest that this probability is a little bit below 1. So this is basically saying that when we consider the TTA, and when we are excluding a fault for at least a period of operation, then the fact that we are considering the TTA means that we are reducing the probability with respect to the assessment that was done for a single epoch, that was not accounting for the TTA at all. But as I said, these are very recent, so they need to be further validated, these results. So to summarize, these initial results appear to show a low value when we're considering the operational exclusion case. So when we are excluding the satellites or set of satellites for the period of operation. We need to, though, determine the impact that this would have on the availability and the continuity. It's only one possible solution to the temporal correlation problem. There are some other possible approaches. So the next steps, we have further steps to take on the theoretical side. The results we have so far have been mostly using an empirical approach. We need to look at whether the allocated integrity risk can be used to bound the risk from the multiple epoch. We need to consider what could happen if the fault is not constant, it is varying with time, and really determine what is the worst case. And one final aspect, we need to look also at empirically, from the empirical data, whether the cross-correlation between test statistic and position error is valid, since we have used that assumption in our work. Okay, I think that's everything. So thank you for your attention. And if you have any questions, please.